Yes. All right. Thank you for the introduction. My name is Taylor Brodbeck. I'm a PhD student working with Drs. Giorgio Prestos and Drs. Rudy Saracino. And this is we're going to end today's session similar to how we started it with a review of Strut-and-Tie models for FRP reinforced deep beams. So to start, what is a deep beam? A deep beam is a common structural element with a shear span to depth ratio less than around 2.5. This is commonly found in pier caps in bridges, but is also found in many building members, such as a transfer girder or a deep foundation. And what's different about these members from slender beams is that they do not follow the assumption, Robert Hooke's assumption, that plane sections remain plane. So here in the top left, you can see a slender member being bent, and you can see that that red line represents a plane section in the beam. And then below that, we have experimental data of a deep beam where you can see that red line is no longer straight after being distorted. And that changes how we should design for things, because most of our designs are sectional methods. And if it's not behaving sectionally, then that is not accurately capturing the behavior of the member. So on the right, you can see different strengths and shear strengths based on how it is designed. And you can see the sectional methods is the solid black line over there. And then at low shear span to depth ratios, following Strut-and-Tie models, you can get much higher shear capacities. So it is an efficient way to design these structures, so far seen when we design them with steel, and then also more accurate of how the stresses are being transferred through the member. So they're often designed with Strut-and-Tie models. Dr. Polak covered a lot of this, but I will reiterate. So this will idealize the flow of stresses through the member as a series of struts that carry the compression and ties that carry the tension. And at the intersection of these struts and ties, we have nodes, and each of these have different capacities. Nodes will have different capacities based on what members are framing into them. For example, if you have a CCC node, that means that you have compression coming on all three faces of the node, and that is going to give you more capacity than a CCT node where you have tension running through that strut and connecting at that face of the node. And if you're being subjected to tension, there will be some softening of the concrete in that area, and therefore a reduction of capacity, and that should be accounted for. So for ACI, as we discussed already, ACI 318 has guidance on the reduction factors that should be used to design these members. And for the tie, you assume that all of the reinforcement will yield, and you can use the yield force of that tie as the capacity of that tie. And then for the struts, there are different reduction factors. For example, a strut fully in compression has a reduction factor of 0.85, and that is just to be consistent. If you were designing, say, a column, then you would rely on 0.85 times the compressive capacity of that column. So your disturbed regions designed with Strut-and-Tie should be cohesive with the regular sectionally designed members of your structure. And for struts in a tension zone, that reduction factor is around 0.4, which was determined based on a series of experimental tests to make sure that you're most of the time conservative with the capacity of that strut, depending on how much softening your strut is being subjected to. ACI 440, Chapter 23 on Strut-and-Tie, is not addressed. When this was brought up in the winter 2022 review of ACI 440, the TAC committee said that this seems to be a large gap, and that the preferred solution for designers would be to add a Strut-and-Tie modeling section. And then the response to that from Committee 440 was that they do not feel comfortable due to a lack of research that would enable them to include Chapter 23 So it is not in there yet due to a lack of research, so the rest of this presentation will sort of summarize what research has been done in order to fill that gap so that it can potentially later on be included in the code. The Canadian code does have some guidance on how to design for these members. This is the Canadian code of steel reinforced structures, A23, and it is pretty similar to the ACI code, except the beta factor that was a discrete value based on if you had a CCT node or a CCC node, or if your strut was in a compression zone or area of tension, is now related to compression softening through this equation here. The amount of strain in the tie that runs through your strut softens the capacity of your strut through this relationship here. And that is related to the strain in the reinforcements and then corrected with an angle to correct for the angle of the strut. And then similarly in the Canadian code for FRP designed structures, they have just a few modifications. The first is that, of course, this reinforcement is not yielding. So rather than taking the yield force, they take 65% of the ultimate capacity, and that is to keep it at a reasonably low stress limit. You're not worried about creep rupture or anything like that. But we're not maxing out the ties and not failing by rupture of the reinforcement. And then the only difference in the compression softening is that this subscript changed from an S for steel in the steel reinforced code to an F for FRP. And then other than that, it stays the same. The assumption is that it does not matter what the material straining the concrete is. It is going to have the same effect on the concrete that it is softening. So there's a series of published tests with and without stirrups. The table doesn't fit on one slide, so here we see the ones that just do not include shear reinforcement. Priority was taken to include beams of as close to full scale as possible. So these are, the majority of them have a depth of 40 inches or greater, and that is because there tends to be a size effect. So having large-scale testing is pretty important. So all of these, well, the first series had a combination of both short and deeper than 40-inch deep beams, and then the second set was all around 4 feet tall beams, and these all did not have shear reinforcement, and then they're also included many beams with shear reinforcement as well in the form of stirrups and horizontal distributed reinforcement. So the failure modes, the codes will typically predict a crushing of the diagonal strut, and that often happens, and this is what that looks like when it does happen. You get a large diagonal crack directly from the inside of the bearing plates to the load plates. And you sometimes get additional crushing towards either end close to the plates. And that is typically the assumed failure mode, but that is not always the failure mode. Some other failure modes we might see is one, flexural compression. That tended to happen in ones that had small A over D ratios, which makes sense because at a small A over D ratio, you're going to get more shear capacity, but for equivalently reinforced beams, you're going to have the same flexural capacity. So as you're increasing your resistance to shear, you have a tendency to run into flexural compression failures. And then one that is more unique, I haven't seen in any papers I've read of steel reinforced deep beams, but did happen in some of the ones here, was a failure that they called shear compression, where due to the flexibility of the reinforcement, the diagonal shear cracks extended pretty far into up the height of the beam and then would turn horizontal, indicating that they were limiting the depth of the compression block and then leading to failure of that smaller than typical compression block at the top. So from the tests of Andermatt and Lebel, they plotted the specimen height versus the normalized shear capacity. And you can see that especially at small A/D ratios, you have an effect of the height, which is why preference was taken to larger depth members. One of the other studies looked at the difference between glass and carbon FRP reinforcement. The majority of the database was glass reinforced, but there are a few tests that have been done with carbon. And what they saw was that if you matched axial stiffnesses, meaning that carbon FRP is much stiffer than glass, but if you reduce the reinforcement such that those products are approximately equivalent, then you get similar capacities because you would expect similar strains in those ties. And this is their force displacement response. So this G8N8 was number 8 bars of glass, which is approximately equal to the axial stiffness of 12 number 4 bars using their carbon fiber FRP bars. And similarly, 8 number 6 bars is approximately equal to 12 number 3 bars when you swap glass for carbon. And the main difference between their responses was that they had different concrete strengths. But if you scaled for the concrete strength, you would get approximately equivalent capacities. And then another factor that Dr. Polak discussed was the influence of shear reinforcement. Here's one series of tests by one author, Mohammed et al., that looked at the same A/D ratio with different types of shear reinforcement. So this one in the middle had horizontal distributed reinforcement, and then this one over here had vertical stirrups. And you can see compared to the one without shear reinforcement that you are able to engage more of this concrete and crush it at peak loads and following peak loads. And we can take a look at what their capacities were as well. So we have the one without stirrups is this one in the middle here, and then horizontal reinforcements led to a premature failure in this case, while vertical stirrups increase the capacity. Their thought is that this has to do with softening because the horizontal distributed shear reinforcement is similar to longitudinal reinforcement at the base, where as you have tension in that reinforcement, that is putting the concrete in tension and therefore softening the stirrup more than if you had neglected it, whereas the vertical shear reinforcement sort of clamps the beam together and increases the capacity a little bit for this case. So how do these beams that have been tested and published in the literature compare with the code provisions? Obviously, ACI 440 does not have recommendations. Sometimes 440 will say, take the 318 factors and say, yes, this applies to FRP reinforced members, or in this case, they decided that no, it doesn't, and they probably made a good call with that because what we see here on the x-axis is the predicted by Strut-and-Tie capacity, and then on the y-axis we have the experimental. So for any point below this diagonal line of unity, that represents an unconservative prediction, which is the case for most of these when they did not have stirrups. And I should note that for this case, the ones with stirrups, the stirrups were just neglected in their prediction. And then if we look at the Canadian code instead, we can see that we get a much better response specifically for the ones that do not have stirrups, where we are pretty much along the line of unity for all of the tests except for a few, and then the ones with stirrups are conservative, indicating that stirrups will increase capacity, which makes sense. How much is not covered in this model yet, but Dr. Polak could assess that for you. And one thing to note that Dr. Polak also mentioned was the failure mode. So some of these seem to be just luck in the fact that, yes, the prediction compared to the capacity was good, but the failure mode predicted was incorrect. It would say shear compression or strut crushing, and then the failure mode would be flexural compression, which is obviously incorrect, but serendipitous that it is correct, close on capacity. So some Strut-and-Tie models to address this. We don't need to speak about this one further, but there are a few that look at including the stirrups in their response, as well as this other one by Chen et al., which also included the effect of the shear reinforcement, both vertically and horizontally, in addition to accounting for the cracked nature of the strut. In this paper, they did not use the softening model that is shown in the Canadian code and in the indeterminate Strut-and-Tie model, but in a similar fashion accounted for the cracked nature of the strut. So that brings us to some future work. So obviously there needs to be some more experimental tests done, including shear reinforcement. So these are some beams that I have built and tested with glass fiber reinforced polymer bars with stirrups distributed through the shear span. And we have tested some of these and have a few more left to test. And we are instrumenting them with full field of view DIC in order to assess the different failure modes such that we can have Strut-and-Tie models that can accurately predict what failure mode we're going to have. So this one failed by crushing at the top, although the Strut-and-Tie model predicted it would fail by crushing at the base of the diagonal strut, and you can see that we are able to see the concentration of stresses with our DIC, as well as with a finite element model. We have the crushing captured here, and by completing this study, we'll be able to fill in some of the gaps that have been left with the published literature so far. So that is all. I thank you for your time.
Thank you. Very interesting, especially for me.
Mm-hmm.
So we have time for questions. Okay, let's start here.
Okay, thank you for a nice presentation. I have a couple of questions. The first one is, when you showed your beams, when you showed the reinforcement of the beams, ACI 440.11-22 says that if you have a depth of a beam more than a certain amount, you have to have skin reinforcement.
Yes.
And you don't have skin reinforcement here. Just because you're doing research, you want to see if you don't have skin reinforcement, probably.
Yes, that is correct. We have, in the ones that did not have, so we tested some with stirrups and some without any, so those didn't have horizontal or vertical, no skin reinforcement, and that was sort of to represent, so these are about a foot wide, they're 16 inches, but if that was like the middle of your transfer girder that is much wider, then you wouldn't have shear reinforcement through there. And then to try to isolate the contribution of just the vertical stirrups. That's why we chose to do that.
And the other question is about the paper that you published here in this symposium.
Mm-hmm.
Would it have the results of these beams?
It does not.
Oh.
It does not. Based on when these special publication papers have to be. So this was about a year ago when we submitted these papers. So there's a session in Toronto where I'll be discussing the results of these beams.
This is in 1 year. Okay. There was some, you were, okay.
I have a question. One question is answering that his question. For skin reinforcement is usually used for the Bernoulli beam, for the regular Bernoulli beam. This is a Strut-and-Tie model, so the criteria for that is we cannot consider that as a skin reinforcement. There is some minimum reinforcement and spacing, we call that cracking reinforcement. That I totally agree with him. You need to have that because you will see some cracking. If you want to do tests, for sure you will see some cracking because you didn't provide any minimum reinforcement based on CSA and ACI. We don't have anything for ACI. So this is something that for sure it's better if you include that because this is the research. This is a very remarkable research. The other thing that again is related to the cracking rebar. I saw in some researchers you mentioned that they didn't have stirrups.
Right, yeah, it was just the longitudinal
So
reinforcement
again,
at the base.
Based on CSA code or based on CSA for FRP, CSA for steel or ACI for steel, we need to have some vertical rebar to avoid cracking. So I don't know why they didn't put any vertical rebar or stirrups in their research.
D regions don't have to have stirrups. You can have a D region without stirrups.
They have minimum. They have
The
minimum.
ECI, no. The beta factor of the ECI depends on if you have reinforcement or not. You don't have to. If it's not, the beta factor will be lower. If you have the reinforcement, beta factor will be higher.
So for CSA, what you have?
For the ECI, yes. For the ECI, you have. But for the ECI, you don't have.
Okay, we have a question from the
Do
back.
you have any direction of your testing and experimentation to give for the committee on what your recommendations were for that, to solve that issue with the guy? Not right now, you're not finished with your experimental studies, but you have a direction of where you're going to go with your recommendations to put in that for that particular problem.
Yes, so this research is partially funded by the ACI Foundation, so there's like a advisory committee involved with that, so they are helping with the direction of what would be most useful for influencing future codes.
But do you have an idea of where that's going? As the researcher, you're
Yes.
studying, do you have an idea where that's going? Can you share that, or not enough testing?
Not yet.
I just wanted to get a projection of where this was headed, because I know that's an issue that needs to be solved. You didn't give me any conclusions to that level. I wanted to know where you were on it. Okay. Thank you.
Sorry.
That's fine. That's in Toronto, right?
Yes.
And in between, she's going to publish a paper in a journal, so I will the results. Any more questions? I have a question. Why would they put, but it's not your research, but why would they were putting horizontal stirrups in the region of the beam? Just for fun, or?
I think to meet
And
that,
how they were anchoring them? Because these ones are going around the reinforcement.
they just had long overhangs like the longitudinal reinforcement, I suppose.
Oh, okay. So they were like skin reinforcement,
Yes.
in a sense, right? And they didn't work that well.
No, it lowered the capacity a little bit.
It lowered the capacity.
Yes, because now you have additional tension from the additional reinforcement through your strut.
Oh, okay. Oh, interesting. That makes sense. Okay. Any other questions? No, then thank you very much.